Hi everyone, I'm Florie Carralot. I'm a final year PhD student at CISA. So today I'm going to discuss this project about using simulation-based inference to extract information about cosmic birefringence and axion evolution from the CMB EB power spectrum. So first, a little bit of context. A pseudoscalar field associated to axion-like particles can couple with photon through Chern-Simons terms. So here, what you see is phi, which represents the axion field. F mu nu represents the electromagnetic tensor of photons, and G is the coupling constant. The presence of this Chern-Simons term in the Lagrangian implies that left and right-handed photons propagate with different velocities, and this leads to a rotation beta of the linear polarization plane of the CMB. This effect is called the cosmic birefringence and induces EB and TB correlation. So this cosmic birefringence effect is a parity-violating mechanism, since T and E are parity-even fields, while B is a parity odd. Now let's look at the axion field evolution. So the axion field is a good candidate for dark energy and dark matter, but would be associated to one of the two depending on its time evolution, which is given by the Klein-Gordon equation. So this Klein-Gordon equation has two solutions. The first one, when the mass is smaller than h naught, so 10 to the minus 33 eV, the axion field is evolving very slowly and is overcome by cosmic expansion. In this case, the axion field behaves as dark energy today. On the other hand, when the field, the mass of the field is larger than 10 to the minus 33, the field dynamically evolves and oscillates around the minimum of its potential. In this case, the axion field behaves as a fraction of dark matter. Now let's look at the implications on the EB power spectrum. So the plot that I was showing in the previous slide presents the evolution of the axion field as a function of the redshift for different axion masses. And we identify two characteristic epochs, the reionization and the recombination. So in the dark energy case that you see in purple here, the field is constant during recombination and reionization. So we can translate it into the EB power spectrum by this relationship, which gives the cosmic birefringence angled at a certain conformal time. And it is given by a difference in field value between the emission time and today. So since in the dark energy case we have a field which is constant during reionization and recombination, we have the same amount of cosmic birefringence at those scales. So the beta at reionization is equal to the beta at recombination. So in the dark energy regime, the EB power spectrum is scaled by a uniform beta, and the shape of the EB power spectrum is essentially similar to the shape of the EE power spectrum. On the other hand, when we consider higher axion masses, like in these blue curves, we see that the axion field evolves during or even earlier than the reionization epoch, and this leads to a smaller cosmic birefringence angle at reionization than at recombination. So reionization is for multipoles smaller than 20. So in this dark matter regime, the cosmic birefringence effect is scale dependent. So all of this to say that constraining the axion mass from the EB power spectrum and use its shape can give indication on whether the axion field behaves as dark energy or as dark matter. However, extracting information from the EB power spectrum implies to deal with a non-Gaussian likelihood at low multipoles. So this is what you can see on that plot. So that plot shows the probability of the estimated power spectrum, EB power spectrum, given a fiducial power spectrum, so from L equal 2 to L equal 5. So we see that this distribution deviates significantly from Gaussianity, and the problem is that its form is typically intractable. So we can't use usual likelihood approaches for parameter inference. So one solution to this problem is that I will present in this presentation is simulation-based inference that I will present in a minute. So this plot was a little bit of a spoiler because this distribution was obtained already with SBI, because one of its functionality is to also to approximate likelihood functions. Okay, so what is simulation-based inference? In general, it designates methods that use simulated data generated from a forward model to infer posterior distribution over model parameters. And the main point of SBI is that it does not require an explicit form of the likelihood distribution. So in general, this is how simulation-based inference method use. In this presentation, I will focus on SBI, which uses neural networks. So the first step in the SBI chain is to sample our model parameter from a prior distribution. We assume that we have a prior knowledge on our parameters and we can sample them. So here we have theta 1 and theta 2. We sample those parameters and we give them to the simulator. So the simulator is a function, a mechanistic model that takes as input parameter samples and output a simulation. So at this third step, you are able to produce simulations for different combinations of your parameter samples. And what you do then is to learn probability distribution that relate your data to your parameters. And especially you can learn the posterior distribution. And what you want to do in reality at the end is that you have an experimental data, an observation that comes from your experiment. And for this observation, you don't know the ground truth parameters. So you can evaluate the posterior at this specific experimental data and therefore infer the value of your parameters. So now I will go through the simulation steps that we did to apply this SBI framework to our problem. So we started by generating parameter samples. So here we consider two parameters, the action mass and beta. So here beta is not a time-dependent cosmic birefringence angle, but instead it represents the amplitude of cosmic birefringence, which is essentially given by the product of the coupling constant and the initial field value. So we sample our parameters, and from these we produce simulation of input CMB EE, BB, and EB power spectra using the biref class code. As an additional parameter, we add a polarization angle miscalibration. I didn't talk about that, but a rotation of the detectors that measure polarization can introduce spurious EB and TB correlations, and this correlation can be confused with the true cosmological signal. So we introduce this polarization angle miscalibration, and therefore we have EE, BB, and EB power spectra that depend on our three parameters. Afterwards, we compute the E and B modes harmonic coefficients of our CMB signal, to which we add a white noise contribution. And after that, we estimate the power spectrum. So these three steps constitute the simulator that I was mentioning earlier, which take as input our three parameters and outputs a simulation of the EB power spectrum. And from this simulation, you can estimate the posterior distribution. So now let's look at the results. So we first consider the simple case in which we didn't include any miscalibration in our simulation. So we used here 100,000 simulation of the EB power spectrum and inferred the posterior on Amphi and beta. Once we have done that, we evaluate this posterior for two specific simulation, for two EB power spectra that have two different fiducial masses. So in orange, we are in the case which is a more dark energy-like scenario in which we have a large reionization bump, while the second case in blue represents a dark matter behavior in which we have a very small reionization bump. So you can see on the left the 1 sigma and 2 sigma contours of in the beta Amphi plane, and we see that the constraints on the action mass are very sensitive to the amplitude of the reionization bump, and we see that depending on the fiducial action mass, two regions of the action mass parameter space are allowed. And especially we see that there is kind of a limit at 10 to the minus 32 eV. And this is due to the fact that in the beginning I said that the limit between dark energy and dark matter scenario is at 10 to the minus 33 electron volt, but in reality, masses below 10 to the minus 32 are not sensitive to a scale-dependent cosmic birefringence effect. So this is a plot from this paper which shows the ratio of rotation angles. So here the beta at reionization divided by the beta at recombination, and we see that for masses below 10 to the minus 32, we don't have a decrease of the reionization bump. And this limit here explains what the transition between our two posterior regimes. Then we did exactly the same, but this time including polarization angle miscalibration. So you can see here the marginal posterior distribution on our three parameters. So we consider still the same simulations. So for the first case, in orange, we see that there is a strong degeneracy between the cosmic birefringence amplitude and the polarization angle miscalibration, which is due to the fact that for such a mass, the cosmic birefringence effect is scale independent and produces the same effect as alpha on the data. The other thing that we can see is that on the posterior on the mass, we have a higher probability for masses smaller than 10 to the minus 32, but still larger action masses are not rejected from this posterior. But for these, we observe that the data prefers a very small cosmic birefringence amplitude and a larger alpha. And this is related to the first point, since for this simulation, our cosmic birefringence effect is scale independent, you can cancel the scale dependence of cosmic birefringence for those action masses by setting beta to 0, and this lack of cosmic birefringence can be compensated by increasing the polarization angle miscalibration. For the second case, in blue, we see that the degeneracy between the cosmic birefringence amplitude and alpha is broken, since for this mass, the cosmic birefringence effect depends on the scale, while alpha is uniform across the multipoles. And the last thing that we can see is that on the mass posterior, we see that only masses larger than 10 to the minus 32 eV are accepted, because in this case, for such a mass, we have a suppression of the reionization bump that cannot be reproduced by masses smaller than 10 to the minus 32. Then we looked at the impact of lensing B modes, because lensing B modes contribute significantly to the variance of the EB power spectrum. So what we did here is to infer the posterior using simulation that do not contain lensing. And then we evaluated the posterior for different EB power spectra, which have different fiducial masses action masses, as you can see with this color bar. So you can see that the constraints are tighter in absence of lensing, as expected, if you compare the upper and lower panels. But more importantly, we see that depending on the true action mass, we have two allowed, let's say we have two posterior regimes which can be used to distinguish between dark energy and dark matter scenarios. So now we have tried to quantify these different posterior behaviors depending on the true action mass. So what we did here was to compute the probability of the action mass to be below 10 to the minus 32 eV for all this posterior distribution. And this probability is essentially equivalent to the probability of observing a scale-independent cosmic birefringence signal and that the action behaves as dark energy. So you can see on the y-axis this probability as a function of the true action mass. So there are different cases on this plot. The dashed line represents the case without lensing and the solid line with lensing. And we considered also here three fiducial values of the polarization angle miscalibration. So what we can see first is that when the mass is smaller than 10 to the minus 32, we have a constant probability, because what I was saying is that those masses are not sensitive to a scale-dependent cosmic birefringence effect. Therefore, these masses are observationally indistinguishable, which leads to a constant probability here. When the mass is between 10 to the minus 32 and 10 to the minus 31, we observe a decrease of the probability as a scale-dependent cosmic birefringence effect occurs. And more importantly, we see that the non-zero miscalibration complicates the distinction between the two regimes, as it is less obvious to identify a decrease of the reionization bump, because this miscalibration induces E2B leakage, translating into larger EB reionization bump. So to conclude this talk, we use SBI to circumvent the issue of highly non-Gaussian likelihood for EB at low L. In our cosmic variance and noise limited framework, the constraints are strongly sensitive to the shape of the EB, which is a primary way of distinguishing between axion dark energy and dark matter interpretation of cosmic birefringence. In a realistic constant, we want to include masking, foregrounds, and instrumental systematics. And in particular, we would like to do this analysis for LightBird-like experiments. So LightBird is a satellite mission that will perform full sky observation. Therefore, we'll have access to the reionization scales of the CMB signal. And the last point, an important point, is that we saw that to reach convergence with our neural network, we needed 100,000 simulation. But in a realistic scenario, including all the complexities that I mentioned in the previous point, such a large amount of simulation would be hard to produce. So in the paper that I mentioned here, which is in preparation, we have shown that using sequential inference allows to reduce the simulation budget by a factor of 3, but we still reach the same performance in our constraints. So yeah, my talk is over. Thank you for your attention, and thank you.